On the night of the 2nd of February, 1943, a short Sterling bomber of 7 Squadron fell out of the black sky above the Dutch coast near Rotterdam. It had been hit during a raid, and it came down broken, burning in places, silent in others. German search parties reached the wreckage before dawn. They expected to find the usual harvest of a shot-down bomber, charred metal, spent ammunition, the bodies of young men who would never see England again. What they found instead was a small cylindrical device, roughly the size of a large tin of paint, blackened by fire but largely intact. It did not look like a weapon. It did not look like much of anything. And that was precisely the problem, because within weeks, the men sent to examine it would come to a conclusion that unsettled them far more than any bomb could have. This little copper object, sitting quietly in a German laboratory, was producing more power at microwave frequencies than anything their own scientists had believed physically possible. They could take it apart, they could measure it, they could photograph every cavity and every strap of wire inside it. What they could not do, for a long and increasingly uncomfortable stretch of the war, was explain how it worked. That single fact, buried in a technical annex somewhere in the Reich Air Ministry's files, tells you something the headline events of the war rarely capture. Britain was not merely staying ahead in the contest for the electromagnetic spectrum. It had, for a period, pulled so far ahead that the enemy's finest physicists, men trained at the same universities, reading the same journals, working from the same laws of electromagnetism, looked at a captured British device and could not reconstruct the reasoning that had built it. This was not a story about a secret formula stolen and copied. It was a story about a gap in understanding so wide that possession of the object itself was not enough to close it. And the reasons why reveal something deeper about how nations really win technological wars, and how close Britain came, in the years before that Sterling ever left the ground, to losing this one before it began. To understand why a small device recovered from a burning aircraft could cause such alarm in Berlin, you have to go back to the strange, quiet desperation of British radar research in the last months of 1939. Britain already had radar. The chain home stations along the coast had given fighter controllers advance warning of German raids during the Battle of Britain, and without that warning the outcome of that summer might have been very different. But chain home worked at long wavelengths, tens of meters, and its aerials were vast fixed structures bolted to the ground. It could tell you that aircraft were coming. It could not easily tell a night fighter pilot, alone in the dark, exactly where an enemy bomber was relative to his own aircraft, close enough to open fire. For that, you needed radar that could fit inside an airplane, and radar that could resolve targets with precision. And both of those things demanded much shorter wavelengths, in the centimetric band, far beyond what anyone had managed to generate with any useful power. This was the wall that stopped nearly every radio engineer in the world. Generating microwaves at centimeter wavelengths was possible in principle. Doing it with enough power to bounce a detectable echo off a distant aircraft, and to do so reliably in a device small and rugged enough to be carried in a bomber or a night fighter, was another matter entirely. The vacuum tube technology of the day, the klystrons and other early microwave sources, produced only a few watts at those frequencies. A few watts might illuminate a laboratory bench. It would not illuminate the night sky over the English Channel. The answer came almost quietly from a physics department at the University of Birmingham. In February 1940, two researchers named John Randall and Harry Boot built a device that took the old idea of the magnetron, a valve that used a magnetic field to whip electrons around inside a chamber, and reshaped its interior into a ring of resonant cavities, carved directly into a solid block of copper. the design mattered enormously. Each cavity acted like the neck of a bottle, forcing the circling electrons to give up their energy in short, synchronized bursts at exactly the frequency the designers wanted. When Randall and Boot first tested it, the results were almost absurd by the standards of the day. Instead of a few watts, their device produced something in the region of 400 watts of power at a wavelength of under 10 centimeters. Within weeks, refinements pushed that figure higher still. It was not an incremental improvement. It was a leap of roughly 1,000-fold over anything the world's laboratories had managed before, achieved by two men working with copper stock, a lathe, and an idea nobody else had quite dared to build. Britain understood immediately what it had. Centimetric radar, powered by a source this strong, could be miniaturized. It could go into the nose of a night fighter to guide a pilot onto an unseen bomber in cloud. It could go into the belly of a heavy bomber and paint a crude picture of the ground below, through darkness, through cloud, well enough for a navigator to identify a city and a coastline even when nothing was visible outside the aircraft. It could be fitted to a warship or a coastal battery to track a U-boat's conning tower at night, a target far too small for the old metric sets to resolve. The cavity magnetron was not simply a better radio valve. It was the key that unlocked an entire generation of military technology, and everyone who understood what it meant also understood that it had to be protected as one of the most closely guarded secrets Britain possessed. And in September 1940, in one of the more remarkable gambles of the war, Britain gave that secret away, but only to a friend. A delegation led by the scientist Henry Tizard traveled to the United States carrying, among other things, an actual magnetron packed in a black metal deed box. American radar research at the time lagged well behind Britain's, and the decision to hand over the country's most valuable piece of electronic technology at a moment when Britain stood alone against Germany and had no guarantee America would ever enter the war was an act of extraordinary trust. It paid off. American laboratories, chiefly the radiation laboratory established at the Massachusetts Institute of Technology, took the magnetron and built entire families of radar systems around it. Resources Britain alone could never have matched. By the middle of the war, centimetric radar sets built on the Randall and Boot design, refined by British and American engineers together, were standard equipment across Allied bombers, night fighters, ships, and coastal defenses. It became, without exaggeration, one of the technologies that decided the Battle of the Atlantic, as convoy escorts fitted with centimetric sets began finding surfaced U-boats in the dark that the submarine's own crews believed were invisible. Germany, meanwhile, was not blind to the field. German scientists had done serious work on microwave generation before the war. A physicist named Hans Hollmann had published research and held patents touching on magnetron-like devices as early as the 1930s, and German industry, principally the electronics firm Telefunken and the radar specialists at GEMA, had built a capable and extensive radar network of their own. The Freya early warning sets and the Würzburg gun-laying and interception radars that guided German night fighters and anti-aircraft batteries throughout the war. But German radar, for reasons of doctrine as much as technical limitation, had settled on longer wavelengths, in the meter band, and stayed there. The instinct in German research circles was that pushing to very short wavelengths brought diminishing returns for the effort required, and without a device like the resonant cavity magnetron sitting on a bench to prove otherwise, there was little reason to abandon a system that already worked well enough to shoot down bombers over the Reich. That assumption held more or less undisturbed until the wreckage of a British bomber gave German engineers a look inside a solved problem they had assumed was, at best, decades away. The device recovered near Rotterdam in February 1943 was part of an H-2S set. the ground-mapping radar that let Bomber Command's aircraft navigate and bomb through overcast skies. It was not the very first fragment of British centimetric equipment the Germans had come across. Isolated pieces of related apparatus had turned up from earlier crashes, and reconnaissance and technical intelligence had picked up scattered hints that Britain was working in this direction. But the Rotterdam find was different in kind. It was substantially intact. It could be examined as a working system, not as a scrap of twisted metal whose original purpose had to be guessed at. German technical intelligence understood at once that they were looking at a functioning centimetric transmitter of a power output that, on paper, their own theoretical work said should not be achievable with the tube geometry in front of them. The device was passed to Telefunken's laboratories for detailed analysis, and it is here that the story becomes genuinely strange, because possessing the object did not deliver the answer German engineers needed. They could measure the copper block, they could count the resonant cavities arranged in their ring, and note the geometry of the anode, and calculate, from first principles, roughly what output such a structure ought to produce. And their calculations kept falling short of what the wreckage in front of them had clearly demonstrably been generating in the aircraft that carried it. There was a gap between the physics they understood and the performance the hardware delivered, and no amount of measuring the dead metal could fully explain where that extra performance had come from. Part of the answer lay in a refinement that had been added to the magnetron design after Randall and Boot's original breakthrough, developed by another Birmingham physicist, James Sayers. Sayers had identified a problem with the early cavity magnetrons. As they were pushed to higher power, the resonant cavities had a tendency to fall out of synchronization with one another, with some cavities oscillating in competing modes that robbed the device of efficiency and threatened to destroy its clean, single-frequency output altogether. His solution was to connect alternate cavities together with fine strapping wires, forcing them to oscillate in lockstep. It was a modification that looked almost trivial to describe. A few loops of wire bridging gaps in a machined copper block. And yet it was the difference between a magnetron that could deliver a few hundred watts unreliably and one that could deliver many kilowatts with stability. Strapping was not an obvious add-on that any competent radio engineer would have devised by inspection. It was the product of hard-won failure, an iteration inside a British laboratory that had already been living with these devices for 2 years by the time a burned example reached German hands. A single recovered unit, especially one that had come through a fire and a crash, did not necessarily preserve every fine detail of that wiring in a condition from which its function, let alone its necessity, could be confidently deduced. There was a second obstacle, less a matter of theory than of craftsmanship. Manufacturing a resonant cavity magnetron to the tolerances required was a job for skilled precision engineering, and by 1943, German industry was under growing strain from bombing, material shortages, and the relentless competing demands of a war being fought on every front. Machining a solid copper block into a symmetrical ring of cavities, evacuating it to a sufficient vacuum, and assembling it with the strapping and the cathode assembly. Correctly aligned was not simply a matter of copying dimensions from a captured sample. Small variances in the machining, in the vacuum seal, in the magnet used to shape the electron flow, could produce a device that looked identical on paper and performed at a fraction of the original's output, or not at all. German laboratories did attempt to build working copies. Some of that effort bore partial fruit later in the war, but it never closed the gap in time, and it never matched the reliability and power of the British and American production models, rolling off assembly lines by the thousand. There was, beneath the technical struggle, an institutional one as well. German radar development in this period was not a single coordinated national effort, so much as a contest between rival organizations, military branches, and personalities, each protecting its own programs and its own access to scarce resources. Telefunken and GEMA had their own priorities and their own relationships with the military and the ministries that funded them, and information did not always move quickly or generously between them. A captured device that demanded a fundamental rethink of German radar strategy, abandoning years of investment in metric wavelength systems, was not a message that traveled through such a structure without friction. Some German engineers grasped fairly quickly that centimetric radar represented the future. Persuading the wider system to reorganize around that judgment in the middle of a war already going badly on other fronts was a far slower and more painful process than simply understanding the physics. The consequences of that delay were not abstract. Through 1943 and into 1944, Bomber Command's aircraft, guided by H-2S and protected by centimetric radar-equipped night fighters, and the escorts of the Atlantic convoys, hunting U-boats with sets German crews could not detect, operated for a critical stretch of the war with a technological advantage the enemy could see, could hold in his hands, and still could not fully reproduce. German submarine losses climbed sharply through 1943, a period the U-boat service itself would remember as catastrophic, and the inability to match Allied centimetric detection was one thread among several that ran through that collapse. German scientists were not incompetent. Many of them were among the finest physicists and engineers in the world. What defeated them was not a failure of intelligence but a failure of time, of manufacturing capacity strained past its limits, and of the accumulated, unglamorous experience that a British laboratory had built up over years of trial, failure, and quiet refinement, none of which could be extracted from a single, scorched piece of copper, no matter how carefully it was measured. By the time German industry had made real headway towards centimetric radar production of its own, the balance of the air and sea war had already shifted decisively, and the resources needed to exploit any late breakthrough were no longer there to be spent. The story of the captured magnetron became, in the years after the war, a case study cited by engineers and historians of technology alike, not as a tale of stolen secrets, but as proof of something more sobering, that an invention is never only the object itself. It is the accumulated judgment of the people who built it, the failures they absorbed before they got it right, and the industrial base capable of turning a laboratory triumph into thousands of reliable units in the field. Britain had all three. For a crucial stretch of the war, Germany, despite brilliant scientists and a captured example sitting on a laboratory bench, had none of them in sufficient measure. And that gap, more than any single battle, helped decide how the war in the air and beneath the sea was ultimately fought and won. If you find these hidden margins of the war as compelling as the battles fought in the open, consider staying with this channel, because it is in exactly these overlooked corners, laboratories rather than battlefields, that some of the war's quietest and most consequential victories were actually won. What remains in the end is a small blackened cylinder of copper, sitting today in a museum case, indistinguishable to most visitors from any other piece of wartime scrap. It gave nothing away simply by being found. It had to be understood, built upon, and multiplied by a nation willing to trust an ally with its greatest secret, rather than hoard it. And that decision, made in a black deed box carried across the Atlantic in 1940, may in the end have done as much to shape the outcome of the war as anything forged in the device itself. The men who examined the wreckage near Rotterdam had, in their hands, the answer to a question that would decide battles they would never live to see the end of. They could not read it. And in that failure to read what they were holding lies one of the quieter, stranger truths of the Second World War. That sometimes the deciding weapon is not the one the enemy fails to find, but the one he finds, holds, and still cannot understand.